We're looking at the trig identities, where basically a trig identity is just a known expression that we can use to simplify more complicated expressions. Now, the ones that we're going to look at, I want you to think of the unit circle here. The identity we're going to focus on first is sine theta is equal to, and by sine theta, I actually meant to say sine negative theta is equal to negative sine theta. This guy is actually a fundamental one, and it's easy, or it's possible to understand where it comes from just by observing the unit circle. Now, if you have a look, any position along the outside of the unit circle can be described as being cos theta sine theta, where this represents our x coordinate, this represents our y coordinate. Ignore the x coordinate for now. When we're observing the unit circle, as theta increases from 0 to pi, the sine or the y value is positive, isn't it? Now imagine that rather than going around the circle in an anti-clockwise way, we went in a clockwise direction. So we started at 0 and we started going backward. So negative values of theta here. What would the value of y be? We're going in the negative direction for theta. We get negative values of y, don't we? Now imagine that if we start off, these are going to be negative here. Imagine that we have a positive value of theta and we start going this, but then at the very end, we negate the result. So we've got positive sine theta, and then we put a negative in front. Between 0 and pi, what sort of values of y would we get? It would be, so they'd be positive, but then we negate them. What do we get? Negative. So this is going to start off between 0 to pi. You get negative values here. And then from pi onward to 2 pi, you get positive values because the negative negates it. That's basically the same as just going around the unit circle in the opposite direction. So this is our first identity for our trig functions. The second one that we have is going to be cos negative theta equals something to do with cosine. Now again, let's employ the same practice here. You start at 0 radians and we focus on the value of x. As theta is increasing, the value of x is positive. Then when it switches over here, it goes to the left of the y-axis, so you're in the negative x-axis values, and it becomes negative, negative, positive. I want you to have a think, would it matter if, rather than going positive theta to begin with, if we just started to go in the clockwise direction, would the pattern change at all?
No, it's still positive.
Yeah, it's still positive. So you go positive, negative, negative, positive. But if you went in the opposite direction, you go positive, negative, negative, positive. So it works out the same. So cos of minus theta is the same as what? Yeah, it's the same as cosine of theta. And these two are our straightforward identities for how we can simplify some algebraic expressions that contain trig. Now the other one, which you've already seen since year 8, if you had a particular teacher, or year 9, is Pythagoras' theorem. I want you to think x squared plus y squared gives us the square of the magnitude of something. Now this is the unit circle, so what's the distance from the origin to the outside of the circle? 1. Now because that's 1, we could say it's 1 squared or just 1. It doesn't matter what we decide it to be. Now the next thing is, think of it in terms of, instead of x and y, think of it in terms of cosine and sine. How would we rewrite this? Rather than writing x and y, how would we rewrite it in terms of cosine theta, sine theta? Any ideas?
Cosine squared
Plus
sine squared theta.
sine squared theta. And this guy over here, this is called the Pythagorean identity. This is one of the things you check for whenever you're doing a spec question. First thing you check for is it the cosine rule? Then you ask, is it an isosceles triangle? And if all of those fail, you ask, is it the trig identity or Pythagorean identity? And these over here are three identities that we may use to be able to simplify some expressions. Now, if you turn your attention to example 1, we have a show question. Show that this side is equal to that, or that side is equal to that. Whenever you're doing show questions, what you want to do is you pick the most complicated side and you reduce it from high complication to low complication. Why? Because it's just simpler to go that way. If you're going the other way, it's like you're trying to add complexity and it's hard to see some of the moves sometimes. So, which side is more complicated, do you think, Matilda? The left side. So what we do is we always start off and go LHS equals sine negative theta plus 2 sine theta. Now, next step, what we try and do is, if there's a fraction, we try and put it all over the same denominator. No fractions, so no worries. After that, I ask myself, look at the angle. Is there a way to make the angle common to what our target angle is going to be? Are any of them different? Think about it. There's theta there, but there's minus theta there. We only want to have thetas. So what should we try and change here? Yeah, we have to employ an identity here to change this minus theta into just a positive theta. If we refer to our rules over here, we know that sine minus theta is the same as minus sine theta. So we can do that substitution. And then it simply collect like terms. Minus 1 take 2 is just going to be 1 sine theta or sine theta. And that's your left-hand side. So your LHS is equal to your right-hand side. And therefore you've shown that that is the case. So every time you go to use one of the rules, you just take one line to show that you've done the substitution. If you really want to be, yes, I did. If you really want to communicate it, you can even state what the rule was, but you don't have to. Okay, this one over here. This could be problematic. Do we have any rules for these? Any rules that we can see on the board? Nope. So what do you reckon we're going to need to do here to be able to show this one? Yeah, we need to think of, are there any other rules? Now, one of the rules that we can employ, and I'm going to do some really great board work here by working in the middle, is I'm going to say that sine of pi on 2, take theta, is the same as saying, and I don't want to get this wrong, okay, sine of pi on 2, take theta, is cos theta, and then we have cos of pi on 2, take theta, is the same as sine theta. we have two more. This one will fit. As you can see, because I'm using my help sheet, we don't use these very often. You just have to know that they sort of exist. But again, using the unit circle, we can actually see what's happening here. I want you to think, if we have sine theta, or sorry, pi plus theta, sorry, pi take theta, then what you're effectively doing is, if it's sine, so you're focusing on the y value, you're starting over here because this is pi. And then what we're doing is we're taking theta away, so we're moving in a negative direction. What that means is that we're starting over here and we're moving backward around the unit circle. This is going to give us positive values of pi, isn't it? Sorry, positive values coming out of sine, isn't it? Which is exactly the same as starting here and going that way, because top half is always positive values coming out of sine, bottom half. You start here and you go this way. You go a full pi radians around and then you dip in the negative. And similarly, if you do it the conventional way of sine theta, you start here, go around and then dip. So that's where I believe this guy comes from. This guy, on the other hand, if you start over here, are you starting in the positive or negatives? Negatives. So it's a total opposite of what you're expecting, hence the reason you get the negative there. You don't have to remember that, but I find when you're learning, it's good to know where it came from. Similarly with these guys over here, think about sine when you're graphing it. If we were to graph sine, it looks like that, doesn't it? And if we graph cosine, it looks like, oh man, there, I guess. So it's always pi on 2 radians out of phase with sine, or they're pi on 2 radians out of phase with one another. So because of that, if you start sine up here, and then you start taking the theta away, so you're moving in this direction, you end up getting basically cosine again. And similarly with this guy, if you start cosine at pi on 2, so you're looking at the x value up here and you start taking away, you start at, oh, that will start at 1. Oh, no, it's the x value. You're starting at 0 and then you're building up. So you're basically delaying the functions by that. So that's where these come from. So the question is, can we simplify to show that this is that or that is this? If it's on the board, the answer is probably yes, unless I make a mistake. What side should we go with, Zoe? Left. Is it always going to be the left? Yeah, no, it's not always going to be the left. If it's not the left, can you call it the LHS anyway? If you really want to. Okay, looking at this, you always want to make it so that their theta is the same as the target theta and the RHS in this case. For us, it's going to be theta. So we need to turn cos pi on 2 take theta into just something theta. And the denominator, cos of pi take theta, you want to turn into something theta there. What one can we tackle first, Zoe? What will we turn it into? Excellent. And then the bottom one, Matilda, what will we turn it into? Excellent. Sine over cosine gives us what? Tan. So you get tan theta. Easy peasy, but looks like a different language. Seem okay? So the questions we're looking at today aren't show, they're just simplify expressions. I've done the show one because I thought it would be easier to know what the target is on the board. For the ones that we're focusing on in the textbook today, it's stuff like this, so it's collecting like terms or using a simple identity, or it's stuff like this where you know that's going to go down to like a theta and you just see what you can do. For part 3, you're looking at factorization. So, it's not up there anymore. Basically, you're looking for your quadratic factorization, so it might be a cos squared plus something or other plus a linear term. Just try and do your binomial factorization on those guys, or your perfect square or your difference of two squares. All good?